are looking at linear second order PDEs. And the first thing that we basically learned to do with linear second order was to put it in canonical form. So I basically learned that there's only three types. And from there, we have branched out a little bit. So we have our three types. We have parabolic, which is where we've been spending most of our time. Hyperbolic, which you took a look at a little bit last time. And then elliptic, which we really haven't looked at much other than we put it in canonical form, and we were happy with that. Then from here we have come over and we've been looking at homogeneous boundary conditions. And we've discovered our way of handling that, and that we can do with separation of variables, and we can solve those. And you've looked at all three of the standard boundary condition situations for homogeneous boundary conditions. And then last time we just got started into what happens if you have non-homogeneous boundary conditions. And we found that, well, in the really nice simple situation where the non-homogeneity was just non-zero constants, that with a simple little transformation we could turn it into exactly the same thing. We could turn it back into just a heat equation with homogeneous boundary conditions, and then we could solve the same way we always have, and everything turned out really nicely. So hopefully that's what we've seen so far. So now the question becomes, well, you can't really count in real life on you always having constant boundary conditions. And so what happens over here when we have non-constant boundary conditions? Well, and I forgot to put one level one here, and that is really up here from canonical form. We took it down to where we only look at the higher order terms. We're looking at homogeneous PDEs as well. So really up here we should put homogeneous parabolic and homogeneous hyperbolic.
The thing equals zero.
That the lower order terms equal zero. Actually, it's not even that good. We've been actually doing something even better. So it's homogeneous, but all of our lower order terms were equal to zero, which is even more restrictive than saying it's homogeneous.
Because if you follow your thing like 3 lines down, you get non-constant, and it's non-constant.
Here I'm talking about the PDE, and here I'm talking about the boundary conditions. So with PDEs you have different, you can talk about whether the PDE itself is homogeneous or not, and then you can talk about whether the boundary conditions are homogeneous or not. And so up here I'm talking about a homogeneous PDE, down here I'm talking about a homogeneous boundary condition. So different object that I'm applying the adjectivity to. And really it was something even more than homogeneous. We were actually saying lower order terms were all zero. So we haven't taken, if you look back, we haven't taken a look at anything other than the basic heat equation or the basic wave equation. And so we've still got some work to do there. So if you look at it and you think we've spent all of that time and we have these horrible restrictions. I mean, the lower order terms are zero and the boundary conditions are homogeneous, in that one situation, we can't solve. And even then, we've been having a little bit of fun trying to do it. So, there's a moral there about PDEs.
What's the moral?
They're hard.
Yes.
the
How is that a moral?
So, so what we want to look at today is we want to come down this little branch over here and say, what happens if you have non-constant boundary conditions? And you had your reading. Just out of curiosity, anybody actually read it? We had 3 people read it, up from none last time. That's an infinite increase. Infinite percentage increase, so I guess we'll be very happy with that.
$50.
All right, so I want to go down here. Let's see, which means I should probably start back there.
Okay, I read that.
Okay.
Raise your hand.
What is
Everybody
it?
smile.
Yeah, we're all on camera here.
Wait, why are we having Matt?
Because Justin might have pneumonia.
Oh,
So,
sorry, man.
yeah,
The camera doesn't work from very far away.
yeah, you might have to move, man, just to make sure you can see the board.
Making me move now.
So let's.
I did.
He's getting commentary.
Yeah, wait till this is on YouTube; it'll go viral.
That's not
So, is T alpha squared
big
d
notes
spec
for me,
x
people.
will just stay with nice lower order terms for equal to
There's
0.
no way you can see that.
Homogeneous, nice heat equation. Now, and to keep things somewhat manageable, we'll actually let one of our boundary conditions be homogeneous. But we'll let the other one be something, say, a little more fun, like sine of t. So physically, you've got a rod, it's hot, we heated it up, we've plunged the one end into an ice water bath, and the other end, we've got a very little blowtorch,
That we're just kind of waving.
and we're just kind of waving, just waving back and forth across the.
It's on a pendulum.
So, well, we're not using Celsius or Fahrenheit. We're using our own new one.
Plunge the first
So-
one into an ice bath, you're using Celsius, because you said it
No,
was
I can
0.
I can define these things anyway.
It's
I want
magical
to.
ice.
Oh, you have to define
It's the
it.
Cox temperature scale. 0 is where water freezes, and who knows what else.
But that passes through 0 and gets lower than 0
Yes,
and higher
all
than
right.
0.
So, well, do you really want me to put a 100 on the end of
No.
Yes.
that? Yeah, I don't either. Okay, so we have that. You can come up with your own scenario for how we're doing it. We're taking it in and out of the bath.
That's colder than 0.
So
Dancing.
we get this. Well, we all know that water's not real.
The Terra is concerned with the physical interpretation.
Yeah, that is kind of our
Let's say we got boiling water and liquid nitrogen. Just keep dumping
It's some
each one.
deep-
There we go.
deep ironies going on here. And x 1 minus x, something like that. Okay. So we have our initial boundary value problem, and we want to solve it, and everything looks good except for that boundary condition. And so we go back and say, what did we learn last time about handling non-homogeneous boundary conditions? What do we do?
Throw on another function that sets that equal to 0.
Yeah, so we're sort of separate from this problem. I want to get rid of that boundary condition, so I'm going to create a new function v, which at 0 I want to still be 0, but at L I want to be sine of t, so that when I subtract this off of u, I end up with homogeneous boundary conditions.
But you also needed to satisfy the PDE.
Actually, that's where life's going to get a little more complicated this time.
Are you
So-
We're going to end up changing.
So we want a v that does this. And in general, when we are looking at boundary conditions here, there's a general way of setting these up that always works. It's called finding a convex combination of these two functions. So no matter what function we have here, what function we have there, we can always make this work out by taking v of x and t, and basically what I want to happen is when x is equal to L, I don't want any of this function to show up. And when x is equal to 0, I don't want any of that function showing up. So I'm going to add these two together, but I'm going to multiply by some expressions that have x's in them, so that when x is equal to 0, this guy disappears, and when x is equal to L, this guy disappears. So it's not too hard to figure out how do you make something disappear when x is 0.
You just times it by
You
x.
multiply by it. So I would have an x, and I would be multiplying times the sine of t, and that way when x is equal to 0, sine of t doesn't make any appearance in my expression. And then I want to add on something, and in this case, this part isn't really going to matter or make sense, because this is 0, but suppose this were not a 0 function. Suppose this was cosine of t, or e to the t, or whatever that might be. So you have some other function sitting over here, and I don't want any of it showing up when x is equal to L.
Just do x minus L.
I just want 1 times it when x is equal to L. So how would I get that?
X minus L.
Times the function.
So, let's see, I think I misphrased that.
And if you want it to equal
I mean, we're just
0.
gonna
It's
add
when x is
0.
equal to 0 that I don't want any of this one showing up. So when x is equal to 0, I want,
That's what we got there.
so that's what we got here. Sorry, I'm backwards. So now, when x is equal to L, I don't want any of this one showing up. There we go. So I'm going to have something times my 0, and ignore the fact that that's 0 for a second. And I need this something to be 0 when x is equal to L.
X minus L.
So, but I also need it to be equal to 1 when x is equal to 0. So in this expression right here, I want when x is equal to 0, I want it to be equal to what?
1.
1. But when x is equal to L, I want it to be equal to 0. So what expression would work?
L minus x all over L?
Yeah.
So, yeah, so L minus x over L would work. And then if I simplify that a little bit, I get what works out as a pretty general expression, which is just 1 minus x over L. Basically, you just find a line that goes through the 2.01 and L0. And so we have that. Now, over here, when x is equal to L, I really just want sine of t. And now when x is equal to L, I'll get L times sine of t. So I don't want just x there. I want x over
That
L.
was why it was floating. I was wondering if something else was going on.
Yeah, well, yeah, the superscript was purposeful. So I need that over there.
It looks perfectly normal to me.
And if you think about these expressions that I've got here, I could plug any functions I want in where the 0 and the sine of t are. And I could plug in any length for my rod, any L that I wanted to. And this would always work out to give me the right function at the right endpoint. The correct function at the correct endpoint. And so, in general, when you take this kind of expression where you have the x over L, the 1 minus x over L times your function, we call this a convex combination of our two functions, sine of t and 0. The reason for the word convex is that this really looks like, if you were to do this, if these were vectors, say, instead of functions, what you'd actually be doing by doing this is x goes from 0 to L, you'd actually be traversing the line from the end of the one vector over to the end of the other vector. And so you're finding the line segment that connects these two vectors together. Alright, so we've got that. That's our expression for V. Very conveniently, since this was a homogeneous boundary condition, that one's not even going to show up, and we have a nice simple expression for V. And now what was the next thing we did? So we found this V, which happens to match our boundary conditions. What do we use it for?
Well,
Nothing. Okay, that was a good one.
Well,
But that was
we
fun.
have a W, we're using W is equal to
So now we come over and we say
minus V.
we're going to create a function W, which is what?
It's it's U minus V.
U minus V.
That way we get a homogeneous boundary.
Now, since we're subtracting here, and since V has exactly the same boundary conditions as U, we know that our new boundary conditions, the boundary conditions for W, are going to be homogeneous, which was the whole purpose of the exercise.
But the PDE will be different.
But now the PDE is going to be different because, well, WXX, that's not too bad. That's going to be U sub XX minus V sub XX, but what's V sub XX?
Zero. It's still 0.
V, if we look at our V function here, it only has an x in it. If I take two derivatives, it's 0. And so this is really just, so U sub XX is equal to V sub XX. Where we run into problems is with W sub t. W sub t is equal to U sub t minus V sub t. U sub t, of course, we don't know. That's the whole purpose of the exercise, is trying to find that out. But V sub t is not 0. V sub t is equal to what?
X cosine t, or negative x cosine t, so we'd add it.
So we would have minus
No,
x
well, it's, yeah, you're,
It's X cosine.
cosine t.
I have a hard time with negatives.
Not to be, no, that's not the word cost.
That's the word cost.
It does.
I suppose to be really good at
Parentheses,
Cosine t.
free profit.
Alright, so now when I substitute in, I have that U sub xx is equal to V sub, or W sub xx. I have that U sub t is equal to W sub t plus x over L cosine t. And so when I substitute that back into my original PDE, what I get is that W sub t plus x over L cosine of t is equal to alpha squared W sub xx. Boundary conditions now, well, W of 0t is equal to U of 0 at t minus V of 0 at t, but that U of 0t is 0, that's 0. 0 minus 0 is 0. And W at L and t is U at L and t minus V at L and t, but we've chosen that. So this is sine of t and that's sine of t. Sine of t minus sine of t is 0. So we got our homogeneous boundary conditions the way we want it. And then we want our initial condition. Well, that would be U at x and 0 minus V at x and 0. U at x and 0 is x times 1 minus x. V at x and 0 is what?
I think it's still.
0.
If I plug 0 in for t, sine of 0 is
0.
0. So this whole expression is 0. And so I still have exactly the same initial condition. Rich?
And that's not always going to happen with
No.
the next combination.
No. Now that came out to, if we had chosen this to be cosine of t,
Right.
then we would have ended up with a new initial condition coming in. Other questions or somebody else had there?
I did. It was exactly the same question.
Okay, yeah. All right. So all we can guarantee when going through this process over here, choosing V this way, is that our boundary conditions are going to come out homogeneous. Our initial condition may change, our PDE may change, everything else may change, but the boundary conditions will be homogeneous. So we've sacrificed a great deal on the altar of homogeneous boundary conditions.
Like your son?
Well, not quite that far, but a large bullock. So this now is our new problem that we need to solve. And we would be really happy, except for one thing. What is causing us sadness?
X over L.
The lots.
Now, this right here. This is no longer a homogeneous PDE.
But you can put it in canonical form, can't you?
It's already in canonical form. Yep, it's just that our lower order terms are not zero anymore. And we suspected that at some point in life we would have to face that.
I didn't expect this. Where did this?
So,
really didn't?
I'm sorry.
Surprise.
I didn't realize it would be such a surprise. But anyway, once we became teenagers, we knew life would become more difficult. We couldn't stay children forever. And so we've got this non-homogeneous PDE, and the question is how to solve it. So we go back to cooking class.
Let's move it.
Point of mathematics is to do what? You have a problem that you don't know how to solve. What do? You reduce it to a problem that you have already solved. Well, sometimes that works just great. That was what we were trying to do in the first place. We had non-homogeneous boundary conditions. We wanted to reduce it to a problem we had already solved, one that had homogeneous boundary conditions. Unfortunately, in the process of moving the pot, the range switched which burner was on.
The range?
Sorry, the analogy is
I'm lost.
Anyway, the problem changed. And so it didn't come out the way we wanted to. So there's another aspect to that reducing things to problems you've already solved, and that is to say, well, I've already solved problems that sort of look like this. I wonder if the solutions I found before will still work. Maybe I just tweak them a little bit and everything will come out good in the wash.
So it's right out of school.
So now we kind of come at it from the other direction. And we say, well, let's suppose that W of x and t could be written as a, well, we always, our previous, I didn't mean to offend her.
Eventually, come on.
I know. She's really upset. I knew when I got done, so far everything we've seen, every time we've solved homogeneous boundary conditions, we've ended up with this sum of some functions of t, which depended on n, and some functions of x, which also depended on n. And we multiplied them together and we summed them up, and that was how our solution always seemed to end up. And of course we had some constants sitting out in front. So that's how our solutions have looked so far. So the question now is, I wonder if we could still get away with the same type of solution, even though the problem has changed a little bit. And things don't look too bad. I mean, W sub x, I can figure that out. W sub t, I can figure that out. The big problem here, and if we had actually taken the time to have you try doing separation of variables on this, the problem is trying to deal with this function right here and somehow get it described in a way that we can actually, it sort of absorbs itself into the problem. And so that's going to take us back to our observation that we made a couple of weeks ago, namely that if you look at the set, when we went and solved the homogeneous version of this, the one without that function sitting in top end, we came up with these functions, sine of n pi over Lx. So we had a nice set of functions sitting there, n equal 1 to infinity. And we made some nice observations about them. What did we observe about this set of functions?
They're orthogonal.
They're mutually orthogonal. And when we got all done, if you looked at it, we were really trying, the last step in the process, we were taking just a regular old function of x, and we were finding the c sub n's so that we could write it as a sum of these sine functions. And so we talked about this thing being an orthogonal basis. For a what's known as a function space, but basically we just think of functions as vectors. And we're thinking that we can write any vector in our space as a sum of these basis vectors.
And is the reason it's no longer orthonormal, because when we started we said it's orthonormal, is that because it's got the pi over L in it now?
No, it's the fact that if you integrate sine of n pi L over x times sine of n pi L over x, you don't get 1.
Yeah.
So you either have to redefine the inner product to not be the natural one, you throw in this weird little factor out in front so that you do get 1 out, or you have to redefine these functions and put a coefficient in front of them so that when you integrate you end up with 1. And I prefer to do neither and just say it's orthogonal. So we have this orthogonal basis for this function space. And so the real question here that we're dealing with is what functions can be written as a sum, from n equals 1 to infinity of c sub n sine n pi over Lx. Now, what can we get away with? When we say this is a basis for function space, well, sure enough, if you add them together, you get other functions. And so there is a set of functions which can be written as sums of these particular functions. The question is, well, how big is that space? What functions can you get away with?
Is it all odd functions?
So you look at it and you say the signs are odd, and that's not, a pejorative term. And so, should our function out here, will it have to be odd?
Yes. So.
Yeah, the only thing that would give us any pause is the fact that we're taking infinitely many of them. And so that seems... so we would expect odd. Now, when we actually look at our problem, our function is defined where?
0 to L?
From 0 to L, that's our domain. And so if I have a function on 0 to L, let's just take our initial condition, for instance. I wrote it wrong. I wrote it as 1. Sorry.
Make the L into
It's L. It's X. So we have that one. Is that an odd function?
Yes. It looks like a piece of a science.
You don't know.
Well, if we actually look at it, it's right over here. Where did I put it down there? It's Lx minus x squared. Is it an odd function?
No.
If you recall long ago, far away, if you want a polynomial to be odd, it has to have what? All odd powers. Can't have any even powers in it. If you want it to be even, it has to have all even powers, no odd ones. So you can go back and look at that. So is this an odd function?
No.
No. Is it an even function?
No.
No. Not any of them. So this guy doesn't have any nice properties. So the question is, can I represent this function as a sum of sines? Okay.
Yeah, you can,
How?
because you can just say, well, we want it to be that value on that interval, but you can piecewise define it so that it's odd or even or whatever else you want it to be.
Yeah, if I really want it to be an odd function, since I don't really care what it looks like, in fact I don't even really define it, for negative values of x or any values of x greater than L, I can do what? I can pretend that this function,
But that would be even.
this would be odd.
That's be odd.
Never mind, I don't know the difference between odd and even.
That's okay.
Most of the world doesn't either, Tara, so you're fine.
Yeah, most of the people think that you're talking about their personality, not their symmetry properties when you tell them if they're odd or they're even. So we get that. So I can redefine this when I look over the entire real line as an odd function or an even function. And so it turns out, and this was Fourier's, one of Fourier's great insights, was that sure enough, you take any nicely continuous function and you can extend it into a function which is representable as an infinite sum of sines or cosines or both. And so we're really, this guy is a basis, in a certain sense, for, turns out to be all square integrable functions.
Square integrable is square.
Yeah, don't worry, that's a real analysis issue that goes beyond our scope. But, more importantly, it works for all nice continuous functions. So if we have continuous or even piecewise continuous boundary values, we are going to have to worry a little bit about piecewise continuous. There's going to be something that happens with the discontinuity that's a little disturbing. But certainly any continuous initial condition we're going to be able to work with. All right, so these guys really do form a basis for continuous functions.
So the answer to your question is yes.
And so, yes, we can get away with it. This, by the way, is an advertisement for second semester real analysis, where you can actually figure out that yes, and you can prove that it really is a basis and that it really works. Everything comes out right. All right. So Math 462 for those of you who want to go on it. So we get this. Well, okay, I should be careful. Math 462, depending on who's teaching.
Wait, who could teach it that wouldn't cover that?
I would suspect, how many of you have had 462? Did you ever cover Fourier series?
Yeah.
Okay.
Could you?
So,
Brother Brown was teaching it then, but there's a lot of things you can pick from.
oh yeah.
So anything could be taught or not be taught. Like you'll probably get into multidimensional space. That's about the only guarantee.
Yeah. You have to do multidimensional stuff, but there's a ton of stuff you could throw into a second semester real analysis. That's why, over my career, how many real analysis classes have I taken? 8.
Oh dear.
8.
And taught how many?
And taught? I only taught it once. I only taught the first semester.
You only taught one
Yeah.
semester?
Yeah, that's why Brother Brown was teaching the second semester.
But you taught me real analysis.
First
This is
semester.
shortly becoming Brother Cox documentary.
Yeah. So, Jason.
What else would you like to do today?
All right. So back to the problem at hand. Our approach is going to be to say, all right, we know that when this was homogeneous, we ended up with these nice functions which actually represent basically any continuous function. So let's come up here and let's replace our psi sub x's with these corresponding basis functions that we have over here. And seems semi-reasonable to believe that then I could pick my phi sub t's so that I could pick up the t dependence in here. And these basis functions over here would take care of all the x dependence. And in the end, I would end up with something that actually works.
So are you going to be able to do it with just signs always, or do we?
No, where did the signs come from?
Oh, because we're doing homogeneous.
Because over here I have
Dirichlet.
homogeneous Dirichlet boundary conditions.
Okay.
Now, what if I had homogeneous Neumann boundary conditions? Be cosines. And we still are trying to figure out what it would be if we had homogeneous Robin boundary conditions.
That's signs.
Since about every one of you, when we did that problem in class, came up with a different answer.
I remember that.
So that one's still a little bit of an open question, what we would end up with coming out of homogeneous Robin conditions. But yeah, which ones I use depend entirely on what type of boundary conditions I have. So here we're going to think, well, let's suppose we could represent W, and now since I know these are going to be signs, I only have to go from 1 to infinity because it's not 0, 0. And I have c sub n, phi n of t, and I no longer have a sign. I have sine of m pi over L x.
Wait. But doesn't sine of stuff that's not zero is not? Never mind, I'm good.
So we have that as our guess, our educated guess as to what our solution to this non-homogeneous PDE might look like. Well, that's fine for the W, but that doesn't answer the problem of what do I do with this guy. If I start putting these in, I mean, I can find W sub t. That would just be equal to what?
That stuff is
that
not
would be
over.
Bn prime t.
Making all sorts of assumptions about the fact that this converges uniformly over 0 to L. We can come in, and this is going to be phi n prime of t sine of m pi over Lx. And then what would W sub xx be?
Minus W times n squared pi squared over L squared.
So the c sub n's will stay. The phis
Okay.
aren't affected by the fact that I'm taking a derivative with respect to x.
Then you get n squared pi
And I
n squared pi
double
squared
do that
L
one.
squared.
So yeah, we're going to end up with, should have left room at the beginning,
Said it at the beginning.
n squared pi squared over L squared.
Has to be negative.
So
No, it's not negative, because,
Yeah,
oh,
that's
yeah,
true.
sorry.
It's to absorb it into your C sub n, which is fine.
well, the c sub n here has to match the c sub n up there, and so I can't
Never mind,
be
don't
absorbing
absorb it.
stuff into
You're
it.
on cosine.
And I'm still on
It's science, two
Sines.
derivations.
back to
Sines.
science. All right.
That is not the same.
So I can put this sum in for the w sub t, I can put this other sum in for the w sub xx. Everything's looking good, except for
Our x over L.
x over L cosine of t. It's the old Sesame Street thing, one of these things is not like the others. One of these things just doesn't belong. Since everything else is a sum from 1 to infinity, I would really like this to be also that way. So what I'd really like to be able to do is come over here and say, okay, I've got x over L. Is it cosine?
Yes.
T. I would like to rewrite that in the same form as the other two, the w sub t and the w sub xx. So I'd like to write this, of course I'm going to need, so I'll call them b sub n here, as b sub n times, some function of t times my sine of n pi over L x. I'd like it to be in the same form. Why? What would that do for me?
It will allow you to combine the summations.
So I could combine all of the summations. I could throw them all over onto one side and I could combine them. Now you're going to have to use your imagination here. What advantage would accrue from doing that?
You could imagine that it had to be true for each statement.
What would I have on the other side of the equal sign?
0.
0.
Make it 40.
So I would have a sum of functions of x and t that's supposed to be 0 for every x and every t. What would that tell you about the term inside your sum?
It has to be 0 every time.
It would have to be 0 every time in order to make that work out. So it's the same thing that we were doing when we derived the heat equation, or we moved all the integrals over to one side, we combined them all in, it was equal to 0, and we said, hey, this integral has to be 0 no matter what. We integrate over, and so what's inside of it must be equal to 0, and that's how we derived the heat equation. Now, same kind of idea. You get them all into one big sum, you say the sum has got to be equal to 0 no matter what t, what x you plug in, well, then every term better be 0. Alright, so we've got that. The question is, can we figure out what the b sub n's should be sitting here?
You can integrate.
It's alright, just like that in front of you.
And
I'll try and get small.
Well, we have our orthogonal basis here. So disturbing things in here. B sub n. What else is disturbing in here?
F of t.
F of t. Unknown things that are just hanging about inside of here. Don't really want an F of t. What would it be nice if I could replace that with?
Cosines. Sines.
Well, that would be really nice, but something.
Is your f of t your x times L minus
That's
x?
0.
No, it's a function of t. I need
Oh,
a
yeah,
function
yeah.
of t to go in here.
T.
T, that'd be cool. But we're being a little too much. But what do we have that's hanging around that is a function of t, but it's arbitrary? I haven't decided what it is yet. The phi of t. So what would really be nice is if I could represent this as some combination of my phi sub n's and my sines. Alright, so we got rid of one disturbing problem with this. The next one is the b sub n's, and that we have a method for doing. What's always been our method for finding b sub n's?
Multiply by the sign.
Right. Multiply both sides by, so we're going to integrate from 0 to L, x over L, cosine of t, and we're going to multiply both sides by the sine of k pi over L x, and then we're integrating with respect to x. And so over here, we're going to have the integral from 0 to L. We're going to be taking the sum from n equal 1 to infinity, e sub n of t, sine of n pi over L x, and then we're multiplying that times the sine of k pi over L x, and integrate. So we multiply both sides by the sine of k pi over L x, and then we integrate over the domain from 0 to L. And
We can pull the sum out, right?
making, again, the same assumptions about the fact that this thing converges uniformly on 0 to L.
That integral is 0 when.
We can pull the b sub n out. Well, be a little careful. We can pull the sum out. Integral of a sum is the sum of the integrals. That's not always true if you're doing an infinite sum, but in this case, we can get away with it. Our functions are nice enough that we can get away with it. And then we have the b sub n and the phi n sub t aren't influenced by an integral over x, and so we get the integral from 0 to L of sine of n pi over L x, sine of k pi over L x dx. But that integral, we know, is
0
what?
except for when k is equal to a.
So it's 0 when n is not equal to k, and then we would have to plug it into Wolfram alpha or something like that
1 over 2L or
to
something.
find out what, is it 1 over 2L?
I don't know. That seems.
For sure it's L over
I think it's L over 2. But we'll put a question mark there, who knows what it is. So I would expect it to get bigger, the bigger the domain got. So I get this, and so that's not bad. That means that this whole infinite sum boils down to what?
B sub k.
times what it.
Not related to Burger King.
B sub k.
Phi k. And
Times whatever that is.
suppose this is L over 2 for a second.
Yeah, I think L over 2 does sound right.
We get that. And then this one over here, I can plug into Wolfram alpha or Maple or Mathematica or whatever, and I can get an expression for it. But this is going to come out as essentially some multiple of the cosine of t. Cosine of t will come out, and we'll just be doing x sine of that dx.
Why is there L over 2 question mark?
Because I haven't actually done the integral to find out if that's true or not.
We're pretty sure it's right.
It's within epsilon.
Epsilon must be very.
Epsilon may be large. Alright, so it's greater than 0, that's all we know. So over here I'm going to get some expression, and so I can solve for b sub k. So we end up with b sub k being the, so we have the cosine of t over L times the integral from 0 to L of x sine of k pi over Lx dx divided by this stuff. So assuming that we're correct, this would be L over 2 phi k t. Alright, so we have some ways, and I could move the t's back over onto this side if I wanted to. But we have some ways of calculating some things here. Still some interesting issues going on. But we're starting to see a little light at the end of the tunnel. And so, I figure I can come back over here, I can write this as a sum. And theoretically, at least, I could find some b sub k's. No one's asked the right question, but that's okay. So if we go back to our original PDE, not original PDE, to our non-homogeneous PDE over there, and rewrite it out,
What do
I have w sub t.
What do you B sub k's have to do with C sub n? They don't. You could just absorb them.
We're going well, we'll see how it all plays out here in just a second now. So we have from n equal 1 to infinity, we're plugging in w sub t, which we've calculated out there. That's our c sub n, phi sub n prime of t sine of m pi over Lx. And then I have plus my x over L cosine of t, which I'm going to assume that I could write as an n equals 1 to infinity of some b sub n's times phi n of t sine of m pi over Lx. And I'm going to bring the alpha squared w sub xx over onto this side. So it's going to be minus alpha squared w sub xx, which is the sum from n equal 1 to infinity of minus n squared pi squared over L squared c sub n phi n of t sine of m pi over Lx. And that whole thing is equal to 0. Now, every one of these sums goes from n equal 1 to infinity, and so I can do what?
Combine them.
One.
So I can combine this into one big sum, 1 to infinity. And then if I kind of look at how things play out here, so I have c sub n phi n prime, phi sub n prime. Everybody has a sine of m pi over Lx, so I'm just going to factor that all the way out. And so if I look at what's left, I have this from the first sum. The second sum is what?
The PC.
B sub n, phi sub n's. And then in the third one, I would have a plus alpha squared n squared pi squared over L squared. That should look vaguely familiar. And c sub n times phi sub n. And I got all of that times my sine of m pi over Lx. And that whole thing is equal to 0. Rich.
So I just want to make sure why we have a plus sign.
This is minus alpha squared.
Oh, because we brought it over to the other side.
That's it, yeah, I brought it over to this guy, so it was a minus alpha squared. Alright, so I have that. Now we do the argument that, well, this is an infinite sum, this is a function of t, this is a function of x, no matter what value of x and t I pick, I'm supposed to end up with 0 coming out. So what has to be true? These things have to be 0.
So now we have an ODE, right?
So this one I don't really care about. I already know it. But what I do know is, so I can say this one over here had better be what? 0. Because this guy, requiring this guy to be 0 for all x and t is a bit much.
Well,
Yeah. So we know that for some x's it's not 0. So this guy can't be 0 everywhere. So this guy has to be 0. So this means that we've got c sub n, phi sub n prime, plus, and both of these terms have phi sub n's in them, so I can just combine that into a b sub n plus alpha squared n squared pi squared over L squared c sub n. Phi sub n is equal to 0. Well, that is an
ODE.
ODE.
First order linear ODE, right?
Yeah, first order linear. Well, in fact, it's even separable.
You can use integrating factors, right?
So you can use integrating factors, or you could separate and integrate.
Do we still need the summation, or are we able to?
No, that's what we took off here, was the fact that since this has to be 0 everywhere, no matter what value of t you pick, no matter what value of x you pick, well, there's certainly values of x where this isn't 0. So in order for this entire sum to come out 0, no matter what value of t I pick, this expression right here has to be 0.
this ODE is going to give us our functions of t,
Yes.
and then we'll go and solve for our
And then we're going to
constants
have to
later.
go solve for our constants.
So I guess my question then is, why do we have the sub n still?
Oh. Sorry.
Because that has to be
So,
true
well,
for every single
has to
one
be
of
true
them.
for all n.
Oh.
No matter what n you pick, this has to work.
Okay.
So all of our phi sub n's have to be solutions to this particular ODE. Alright. Now, like I say, this is a separable ODE. So we bring this over here and we divide by phi sub n. I would have d phi sub n over phi sub n is equal to, well, if I bring that over, I'm going to have minus b sub n plus alpha squared n squared pi squared over L squared c sub n divided by c sub n times dt. And so I can anti-differentiate each side. And we end up with, so we go over here. So we have the natural log of phi sub n is equal to that lovely constant times t plus another constant.
And then we'll
So yeah, we got to do something with these constants. And so we're going to have minus, and we have b sub n plus alpha squared n squared pi squared over L squared c sub n over c sub n
do you have to factor that?
times t plus k.
There's parentheses around the numerator.
Well, technically it should be.
And should there be parentheses around the numerator?
Don't need them. You can put them there if you'd like, that's fine. Well, so we take e to both sides, and we end up with phi n of t is equal to, well, some, we'll keep calling it k sub n. Technically it's e to the k sub n, but that's still an arbitrary constant. Times e to the minus, and if I simplify this a little bit, well, I have b sub n over c sub n here, which I'll leave it that way because it's easier to see at the moment, but an arbitrary constant divided by an arbitrary constant is
Still an arbitrary.
pretty arbitrary.
Solve.
Now, the b sub n and c sub n's played slightly different roles over here, but we can see kind of how to wash that out. And then over here, those would cancel. I would just have alpha squared n squared pi squared over L squared
times t.
Did you minus all that? Oh, gotcha, and then minus t.
So what I have basically is I have this constant expression here, part of which comes from the eigenvalues for my eigenfunctions that I used as part of my expansion, and times a constant. And now so I found my phi n sub t's. Put those back into my expression for w.
Apply the initial condition.
And the k c sub n times k sub n's, well, I could absorb that. That's just an arbitrary constant. And now I can go apply my initial conditions and try and figure out what those constants ought to be. So, lots of details, but let's get back to the key observation. Key observation is that these functions that I found when I was doing homogeneous boundary conditions with a homogeneous PDE, these functions I found over here really are a nice basis for a function space, for a very broad function space. And so I can take really any function and write it as a linear combination of these basis functions. And so that's our observation with W, is the idea that, okay, I'm going to take this I sub x's, I'm going to replace them with these basis functions over here. And I'm going to write both W as, linear, we're stretching the definition of linear, but linear combination of these signs. And I'm going to write my non-homogeneous part, my forcing function, for those of you who are in physics, as I'm going to expand it out in those eigenfunctions. And then when I put it all together, that gives me compatible sums that I can piece together, and then that gives me the ODE that I need in order to actually solve out and find the solution to my initial boundary value problem. Rich.
So basically we just say, well, the size are going to be the same, because the way that we've defined W is not going to mess with how we get psi. And then we say, well, since I know what W is, I can take its partial derivatives. And then we just say, well, since everything's a sum, we just find a sum for that last, or for just the lower order terms.
So, yep, the key idea is I'm going to represent everything as a sum of these signs.
And then that will always does it always turn into a first order ODE? I guess with this one it will.
With
the wave equation, it would turn
with the
into
wave
a second
equation, it would
order.
turn into a second order
Okay.
ODE. But what we've done, and this is, if you look back at everything that we've done, what we're doing is we're finding various ways to get rid of one of the variables. Either we split them apart so that we can treat them separately so that they're ODEs, or in this case, we just assume we know what happens with the one, and then the only one left is 1, so we end up with an ODE coming out. Tim, and then Forrest.
So what I'm seeing here, I'm trying to write down the answer, but we have a bunch of constant sub n's that are in front of our different equations that we're putting together. I assume we could just smash all those together to a c sub n, but we also have this other one in the exponent.
Yeah.
So do we have a different one? So we have like a b sub n still?
That's an interesting, yes, we're going to have to deal with that. So I want to be thinking about how can we get rid of that. We're already over time, so I'm not going to tell you right now.
Okay.
But yeah, we're gonna. What do we do with that guy?
And my observation was just that looks awfully like what our phi sub t was before, except we had this other
We have this little extra stuff.
thing.
That's
So when t goes to 0, our exponential doesn't go to 1.
Right. Very good. Which is a nice observation. All right. Well, sorry I took you over a couple of minutes.
It always happens.
It's PDEs. I'm sorry.
No, it's fine.